Assalamu alaikum. My name is Khaled and I'm honored to be the presenter of this paper titled Contribution to the Optimization of the Flight Duration of Autonomous Drones Flight Path Planning. I'm affiliated with Ibn Tufayl University, where I have been actively involved in the research process with my co-author Dr. Ouadoudi Zytoune. Their expertise and contribution have been invaluable in shaping this paper, and I hope it will be equally valuable to all of you. But first, let me provide you with an overview of what we will cover during this presentation. We will start by introduction, then problem statement, motivation, system model, our contribution, simulation result, and finally, conclusion and future work. Let's begin with an introduction to provide you with an understanding of the context and purpose of our research. Unmanned aerial vehicles, or drones, have gained a lot of popularity over the last decade. The use of autonomous drones appears to be a valuable and low-cost solution to problems in many applications. Path planning capabilities are essential for autonomous control systems, although previous research papers propose a mixed programming model to address this challenging problem. Given that drone can perform multiple supports for many base stations, this raises different questions as how to manage the cost of service and how to minimize the time service, including capacity of the drone, while maximize the quality of the service. In this study, we began by approaching the question as a single solidarity problem mathematical approach. A dual approach was then used. A heuristic approach and a meta-heuristic approach, a new version is presented. A mixed approach is needed when trying to solve a single target problem. This problem has been a persistent challenge in our field, and it requires an innovative solution to overcome its impact. The foundation of all routing literature is vehicle routing problem. This is a well-studied area that is still very amenable to new technological advances. The problem revolves around optimizing the flight duration of autonomous drones through flight path planning, specifically focusing on the vehicle routing problem and its relevance to unmanned aerial vehicle. Three main aspects that seem particularly relevant when dealing with UAV vehicle routing problem. Problem type. When classifying route-related literatures, we can focus on vehicle routing problem and classify it by problem type. Transportation, because the characteristic of the mode of transport, land, sea, air, and so on, transport mode have been different characteristics in terms of cost, transport time, accessibility, and environmental performance. And last but not least, degree of automation. The degree of automation of a transportation system is one dimension, as automated systems are discussed in dynamic vehicle routes. The motivation behind our research stems from the potential implication of solving this problem. The problem of routing vehicle has been extensively studied in different fields. It aims to determine the optimal routes for a fleet vehicle to serve a specific group of customers. It introduced first in 1959 by Dantzig and Ramsar by how a fleet of homogeneous tracks could supply the oil demand of multiple service stations over a distance traveled from a central point. Then in 1964, by Kosowski, Gola, and Amela, they generalized this problem to a linear optimization problem called vehicle routing problem, one of his most studied topics in operation research. The main goal of vehicle routing problem is to minimize distribution costs and find the shortest route between points. To tackle this problem, we develop a comprehensive system mode in this system. In this system, we consider a network composed of n bus stations, a starting and ending repository for UAV. The set of bus stations is donated by 1 tel n, while the starting point is set to 0, and the ending point is referred as n plus 1. In the case of having the same report for the starting and ending, we can use interchangeably indices 0 and n plus 1. First, UAV that are of number k are in starting repository, and upon request, they travel to bus station for serving, giving support for demanding bus station. The travel from starting repository to a bus station, between bus station, and from bus station to ending repository cost is donated as SEG. I represent the source node when G the destination node. Let note X are AG and Y are A. Binary variable represent respectively if the arc AG and bus station E belong to route R, where a route R is a sequence of visits to a subset of bus station that is noted NR, given as subset of N and R. Is the set of all feasible routes. We assume also that all UAV are homogeneous, rated their capacity of service. This capacity is constrained by their energy reserves. We denote by Q this capacity. The total required service is QI, and the service duration is SI. Let G the directed graph that models our system. Now let's move on to the contribution of our research. Through our study, we have made several significant contributions to the field. First, this work focuses on the vehicle routing problem with time deadline for a single deposit with time constraint. The goal is to determine the number of vehicles and routes under time constraint to maximize the total profit of the visiting customer minus the travel expenses. For this problem, we propose a model called AMPI already proposed. A heuristic method can be used to find optimal routes. These routes can be re-optimized based on marginal profit. Consider a base station I. We defined its marginal profit as Ni, with K and L are the nodes that respectively precede and succeed node I in the same route. A negative marginal profit of a bus station I means that the bus station is not interesting to visit. In this work, we consider that SEG are proportional to dig. The IMPI algorithm is given in the following. The algorithm 2 details our proposition. We propose to find an optimized route to visit and deserve all bus stations. We use simulated annealing algorithm for this purpose. For this route, we apply the marginal profit to exclude bus stations that not contribute positively to the total profit. The clean route without bus station with negative marginal profit is used hereafter for selecting definitively nodes bus station to keep based on the drawn selecting definitively nodes to keep based on the drawn capacity. The last problem is known as key knapsack problem. The nodes that are excluded in the first or in the second step are considered in a novel iteration to find route to the second drawn, and so on, until considering all nodes and or all drawns. Next, I would like to present the result of our simulation, which provide as table 1. Table 1 demonstrates the variation of total profit and route number with time of service Ti equal 100, where route number refers to the UAV number. Reducing the time of service Ti clearly reduces the total profit of the model and improves efficiency. With the addition of a number of autonomous drones, we still maximize the profit. In the following table, we assess the impact of number of bus stations considered an instance of a vehicle routing problem with time of service Ti equal 100 and number of drones equal 4. Table 2 describes the variable represent possible vehicle route in the network model, while increasing the total bus station increases the total profit of the model and improves efficiency for each route. Using the simulated annealing algorithms, we obtain the best solution for the drone routing problem. Additionally, we employ the marginal profit function to remove unnecessary base stations from the solution, resulting in a cleaner route. This cleaned route is then visualized in our first graph, showcasing the best solution route. To select the appropriate items for the cleaned route, we utilize a key knapsack algorithm that reads the bus station data and identifies the corresponding items. Subsequently, an exhaustive algorithm which exhaustively solves the key knapsack problem is applied to determine the optimal combination of items like bus station that adhere to the drawn capacity and service duration contract. Lastly, the code identified the remaining bus stations that were not visited in the current iteration, allowing for further analysis or decision making based on this information. Developing an efficient and robust drone path planner with low computational cost can be challenging. The drone path planning problem is related generating a cheap collision-free path between start and end point. Our future work is developing of heuristic, meta-heuristic, or approximation algorithms to solve models of large problems in reasonable time, combine our approach with multitasking reinforcement learning or transfer learning, and finally implement and test the algorithm in realistic environments. Thank you for your attention, and if you have any question, you are welcome, and thank you.